Hello and welcome. In this video, we're going to talk about implicit differentiation, what it is and how to do it. So what we have been working on so far is finding the derivatives of equations that express one variable in terms of another. So for example, y equals 3x squared plus 5 is an explicit equation. Explicit because y is defined in terms of x. And if we found the derivative with respect to x, or if we found dy dx, we would apply the power rule to get 6x and we would be done. That's explicit. Implicit shows an implied relationship between two variables. So here on the right-hand side, we have an implicit equation. We have x squared and we have y squared, and they are related to each other, but it's not y equals something. It's an equation that involves both of them. It's actually the equation of a circle. And we know that we could find different tangent lines, which is what the derivative really is. We could find different tangent lines of a circle going around it. And that would depend both on what's happening with y and what's happening with x. And that leads us to, well, how do we take the derivative of implicit equations? And we do that using implicit differentiation. So using implicit differentiation, if a function is not defined as one variable, or y equals one variable, anytime we differentiate, we have to add a penalty term, or we have to add an extra term. Typically, that's going to be dy dx or dy dt. Basically because we're applying the chain rule. So what I mean by that is, if I was taking the derivative of this equation of a circle up here, and I'm taking the derivative with respect to x, I'm applying d dx on both sides of the equation. When I do that with x squared, I just take 2x, and that is in terms of x. So I took the derivative in terms of x of something that was x. If I take the derivative of that in terms of y, well, if I take the derivative, I get 2y. But that's the derivative with respect to y, and we're supposed to be taking the derivative with respect to x. So anytime you're taking the derivative of a variable with respect to a different variable, you have to tack on this little penalty term, which is basically just using the chain rule. So because I took the derivative with respect to of y, and I was supposed to be taking it in terms of x, I have to just multiply on this dy dx term. I didn't have to do that with my x term because x was the variable I was taking the derivative with respect to. So let's go ahead and finish this problem off. If I take the derivative of 9, the derivative of any constant is just 0. So now what I have is 2x plus 2y times dy dx equals 0. My ultimate goal is to get the derivative, so the next thing I'm going to do is I'm going to isolate dy dx. So I'm going to subtract 2x on both sides, so 2y times dy dx equals negative 2x because I subtracted it on both sides. And then if I want to get dy dx by itself, dy dx, I'm going to divide both sides by 2y, which the 2's are going to divide to be negative 1. And I'm going to have an x in the numerator and a y in the denominator. So notice we now have a relationship that still includes both x and y. So if I was going to evaluate this derivative, I can't just evaluate it at an x value. I would need to be able to evaluate it at an ordered pair. Like, what is the equation of the tangent line at the point 2, 4? And then I could plug in 2 for x and 4 for y. So the basic idea, take the derivative the way you always would. All those basic standard differentiation rules apply. The chain rule, the product rule, the quotient rule, the power rule, all of those rules still apply, but anytime you're taking the derivative of something that's not the variable you're taking the derivative with respect to, you need to add on a dy dx or whatever it happens to be, and then in the end, isolate that portion of the problem. So let's work through some more examples. So in the directions, we are being asked to find dy dx. So I'm going to take the derivative with respect to x of both sides here. So d dx of both sides. The derivative of x is 1. The derivative of y is 2y, but we're taking the derivative with respect to x. So anytime it's not the right variable, I tack on a dy dx. Now I just need to isolate dy dx, so I'm going to divide both sides by 2y. And that's going to give me that the derivative with respect to x is 1 over 2y. Okay, number 2, I'm taking the derivative with respect to x. Go ahead and see if you can do the first step. Remember, anytime you take the derivative of something that's not x or not a constant, you need to tack on that penalty term of dy dx. So go ahead and pause the video. All right, hopefully you have had enough time to pause the video. The derivative of x is 1. The derivative of y squared is 2y, and that's going to get this dy dx. And that's going to equal the derivative of 3 is 0. And now I'm just going to isolate dy dx. So I'm going to subtract 1, and then I'm going to divide by 2y. When we get to number 3, there's a chain rule situation happening here. So I'm still going to take the derivative with respect to x. Notice this function on the left has an outside function, stuff squared, and an inside function, x plus y. So I'm going to take the derivative of the outside function, 2 times stuff to the first power. Since there's no variable here, when we're thinking about the outside function, I don't need to tack on a dy dx. I keep the inside function the same because I haven't taken the derivative of that yet. I took the derivative of the outside function. Keep the inside function the same. Then I'm going to take the derivative of the inside function. Well, the derivative of x is 1. The derivative of y is 1, but we also need a dy dx, since now I am taking the derivative of y with respect to x. The derivative of 2x is going to be equal to 0. So now I need to solve for dy dx. I'm going to divide both sides by 2 times x plus y. So I'm going to have 1 plus dy dx equals, if I divide by 2, the 2's are going to go away. So I'm going to have 1 over x plus y. And then I'm going to subtract 1 on both sides to isolate dy dx. So 1 over x plus y minus 1, that's going to give me my derivative. Let's look at some more examples. All right, I'm going to encourage you to pause the video and see which of these 3 problems you can work through on your own, and then unpause the video and see how you did. Number 5, I want to point out, has a product rule happening here, so be careful if you work through that one. All right, hopefully you have had time to work through this. I'm going to take the derivative with respect to x. The derivative of cotangent is negative cosecant squared of y. Now we just took a derivative with respect to y, so this needs to be multiplied by dy dx. And that's going to equal, the derivative of x is 1, and the derivative of y is dy dx. So I want you to notice, hopefully you at least got here, but we actually have 2 dy dx's now. We need to, in order to solve for dy dx, we need to get them on the same side. So I'm going to add this to both sides. So I have dy dx minus cosecant squared y times dy dx, and that's going to equal 1. Now, how do we isolate dy dx? Well, both of these terms have a dy dx, so we can factor it out. If I factor it out, I get negative cosecant squared of y plus 1. Sorry, I get 1 minus that. Let's do it that way. So the 1 is coming from factoring it out here, and the negative cosecant squared is coming from factoring this one out. So that's going to equal 1. And now I can just divide by that thing I just factored out, 1 over 1 minus cosecant squared y. And there is some trig identities you could use here, but that's not really the point, so I'm going to leave it just like that. Okay, number 5. So when I take the derivative with respect to x, which I'm going to do everywhere, of this part, I'm going to put the 2 in front. I'm going to deal with the x and y separately because I need to use the product rule. So the derivative of x is 1 times y with the product rule plus x times the derivative of y, which is 1 dy dx. Plus, if I take the derivative here, this is going to be 2y times dy dx, and this is all going to equal 0 because the derivative of 3 is 0. Now, I need to get my dy dx's together. So I'm going to actually simplify this. I'm going to say 2y plus x dy dx plus 2y dy dx equals 0. I'm going to put 2y on the other side, x times dy dx plus 2y dy dx equals this 2y, negative. Now, I'm going to factor dy dx out. Dy dx times x plus 2y equals negative 2y. And then I'm going to divide both sides by that factor. And now I have solved. All right, number 6, I'm going to take the derivative with respect to x of both sides. The derivative of cosine of y is negative sine of y, dy dx. The derivative of 1 is 0, the derivative of x is negative 1, and the derivative of 7 is 0. So I'm going to add 1 to both sides. Negative sine of y dy dx equals 1. And I'm going to divide by negative sine. So dy dx equals negative 1 over sine of y, or negative cosecant of y. We're going to look at a few more examples. Okay, the first thing I want to do on number 7 is actually just rewrite it using rational exponents. So y squared plus 2 all to the power of 1/2 equals 5x. Now I'm going to take the derivative of both sides with respect to x. Notice there's going to be a chain rule situation here. So 1/2 times what's inside to the power of negative 1/2 multiplied by the derivative of the inside, which is 2y, but don't forget you have to tack on. It's like you're taxing it. You have to tax it dy dx. Equals 5, because the derivative of 5x with respect to x is just 5. Now, I'm going to simplify this a little bit. This 2 and this 1/2 are going to multiply to be 1. So I have y times y squared plus 2 to the power of negative 1/2 times dy dx equals 5. And I'm going to divide both sides by all of this stuff in front of dy dx. So y times y squared plus 2 to the negative 1/2 power. And you could also move this term into the numerator and make it the positive 1/2 power, but I'm going to leave it just like this. What we're going to do next, we're going to do 2 more examples that are going to build on this idea a little bit. We're going to extend it and say, what happens if we want to find the derivative of this derivative, or what happens if we actually want to find the equation of a tangent line? We will do more practice like these problems in class, but today I really just wanted to give you a little sneak peek on where we're going. So let me clear some space for this. All right, here we go. The very first thing I want you to do is take the derivative with respect to x here. So go ahead and pause the video and work through that. So hopefully you got here, and this was actually a lot like the very first problem that we did today. Suppose that we're being asked to find y double prime, which means what we really need to do is take the derivative of this derivative. That would give us y double prime, which is also could be written as d squared y dx squared, which literally just means do it again. If we do it again, what we have here is a quotient rule. So we take the derivative of the numerator, negative 1, we multiply it by the denominator, we subtract, keep the numerator the same. The derivative of the denominator is 1, but then we have to tax it, so throw in a dy dx there, all over the denominator squared. Now the key thing here is that your final answer needs to not have, I'm just going to write y double prime, needs to not have dy dx in it anymore. It should be solely in terms of x's and y's. So let's simplify. This just becomes negative y plus x times dy dx all over y squared. And what we're going to do lastly is we're going to plug in what we know. We know that dy dx is negative x over y. So this is really the same thing as negative y plus x times negative x over y all over y squared. Now I don't have a dy dx in here anymore. And we could simplify this just a little bit more. I'm going to split my fraction. So this is going to be 1 over y. This is going to be minus x squared over y to the third, because there's 1 and 2 more in the denominator. Now, if I was asked to evaluate this at a particular number, I could just plug in that number for x and y. All right, last example, and don't worry, we will do more of those in class. Determine the equation of the tangent line to the graph at this point. So we already know our final answer is going to have that ordered pair plugged in. What we need to find is the slope at this point. So what is the slope? The slope is the derivative. So we're going to find the derivative with respect to x. So 2x plus 8y dy dx equals 0. I'm going to subtract 2x and divide by negative 8 or by 8y. So that's going to give me negative 2x over 8y, which simplifies to be negative x over 4y. I'm going to evaluate that. This line just means evaluate. I'm going to evaluate that at the ordered pair that they gave me, which is 3, 2. So I'm going to plug in 3 for x and 2 for y, and that gives me negative 3 over 8, and that's the slope that I'm going to plug in over here. So let's recap what we did in this lesson. We talked about how the type of differentiation we have been doing is explicit differentiation because we have one variable and we're differentiating with respect to that one variable. We talked about how there are lots of implicit functions that also have tangent lines and how to work through finding the derivative implicitly, meaning anytime we're taking the derivative of something that is not the variable we're differentiating with respect to, we have to tax on a little penalty term like dy dx or dy dt. The rest of our rules for differentiation still apply, and then in the end, we're going to solve for dy dx. This still comes into play when we have chain rule, product rule, quotient rule, just power rule. All of those situations still apply here. And then lastly, we extended this idea to what happens if we need to take the second derivative, or what happens if we're tying that back to equations of tangent lines. So go ahead and write down any questions you have. I look forward to supporting you on this. Thanks for listening.